I feel that the monopole needs an explanation because people really don't understand I think what I was trying to accomplish and what the meaning of energy actually is. So I'm going to start out basically with just a simple little drawing here. And I'm actually going to put it up this way. What I'm going to start out with is just a wheel and two simple magnets and both north poles. So we all know that if you want this wheel to spin, that you either have to put another magnet here to force this one away, or you have to put a magnet here to attract it in. So, but instead, what we want to do is we want to put a coil here. And we're going to sort of draw the coil like this. And we're going to call this the power. Power winding. We're going to call this the trigger. Okay, so we wound our coil, and when we're winding our coil, what we want to do is we want to stretch out our wire, and we want to sort of wind like this. So you're laying them out, and the drill's twisting them nice and tight. And depending on how many, you could have 3 or 4 or 5. Depending on
so you put the ends of the wire in a drill chuck.
Yes, and you twist them all together. And it doesn't make any difference whether you start winding at this end or this end, because I know that question's going to come up. What end do I start at? Doesn't make any difference. Okay, so we know we got an iron core in here, and we don't want a solid iron core. I see a lot of people just taking a bolt and just cutting it off and using the bolt. We don't want a bolt. We want individual little rods. And the reason that we want individual little rods is we don't want all the currents building up in here heating the bolt. Because when you use a solid material as the core, you cause these little circulating currents, which are called eddy currents, to generate heat. So we want to break up that by using individual rods. Okay, so.
Sound okay?
Okay. So the next little step to our motor that we want to do is we want this machine to rotate. And when we talk about the monopole motor, we're not talking about a motor that can spin a water pump at Boulder Dam. We're talking about a motor that's going to be used as an energizer, because we're looking for a certain energy to come out of this motor and give us 23% mechanical. Max. That's the max you're going to get out of this motor.
How do you know that number, John?
because we measured it with a dynamometer. And we know that the maximum that we can get out of it is 23%, which is more than enough if this is the pulley and there's a belt going from here to here, it's more than enough that it can drive something out here, whether it be contactors, whether it could drive a water pump out here, but it has to be geared correctly, and this has to be at maximum speed. So we're not going to go into that. We're just going to go into the motor. So anyway, we know that we want this to turn, and we know that if we took these leads and we just put a battery out here and we just hook that up, all it's going to do is push this out of the way or attract it and heat the coil up because it can't go off. There's no switching to it. So we can't do that. So what we have to do is we have to devise a very unique switching circuit to make this motor go. So one way to do this is if we want to use a PNP, we would put a PNP transit. And a PNP is designated like this.
P stands for what? And N stands for what?
PNP, transistor.
Okay.
Positive, negative, positive.
Okay.
Okay? But we don't want to use the PNP because we want to be able to capture a different form of energy. We're not looking for the normal form of energy. We're looking for a different form of energy. We're looking for a form of energy that is basically currentless. We don't want any current. We want the current to build in here, but we want to shut this current off. We want this current to build a magnetic field, but we're going to shut it off right away. So, what we want to do is we want to use just a basic NPN transistor. And of course, in this loop, this is the ground. So, we know that we want to connect the battery. And we'll just put that one to ground. These two grounds match. So just think of a line between them. Okay, the next thing that we want to do is we want this wheel. We're going to move these magnets. So if I move these magnets, we want, when the wheel moves, we want this magnet to be attracted to this iron. Now, as this magnet, which has a field around it, comes into this iron pole, it's building a field inside this coil of wire. And we're going to use that field to turn our transistor on. So very simply, we would just come like this with a resistor. And I'm telling you where to start. 680 ohms. I don't want you to put a 47 ohm there. I don't want you to put a 10 ohm there. And I don't want you to put a 100 ohm there. I want you to start at 680 ohms. I want you to get as much wire as you can get on this bobbin that you're building the coil out of. I want you to get as much wire as you can. I want you to fill it. You don't have to count the turns because you're going to tune it. So it's not important. Then I want you to put a diode in here. And you notice these are all going to ground. That means this ground, this ground, this ground. And what this diode's going to do is it's going to clamp the transistor on the reverse spike. So the symbol for the battery is this, plus and minus. And I want 12 volts here. So I want something like a motorcycle battery. I don't want little bitty batteries that are this big that you buy because they're $3. Because you're not going to gain anything with a battery that's this size that's going to give you 1.5 amp hours. You're not going to be able to run the machine long enough to see anything. So I want a big battery. I want a garden tractor battery. I can't make this any plainer. I want a big battery. I want at least 13 amp hours. It's mandatory. And the charge battery, I want at least 13 amp hours. So, next step.
Wait a minute, just to clarify, you want both batteries to be 13 amp hours?
I want both batteries. Both.
Right.
Now, the reason that I want both batteries at 13 amp hours is so you have time for the machine to see how the machine works. And you don't have to worry about, well, geez, in 20 minutes this battery ran down and I didn't get anything. That's right, you're not going to get anything. You're not giving nature long enough time to do anything. Nature's not going to come right in and charge your battery over there instantly because she doesn't work that way. She works very slow. So anyway, back to this. We want this to come in and charge this iron pole. And we want enough mass weight on this wheel. We don't want a roller skate wheel. We want something that's got a little bit of mass to it. Now, I know that a lot of people out there have made roller skate motors, but it's not buying you anything. You're not getting the advantage of the mass in this wheel. So we give it a start.
You're talking inertia, really.
Inertia.
Right.
But mass weight.
Right.
In other words, we want something that has a little bit of mass to it. Say, we don't want, say, 4 ounces. We want more like a pound. All right? So, because we want the thing so that when you give it a spin, it can carry itself around until you can figure out and get this trigger circuit operating to optimal, which means that it's going to operate in this bell curve. And we want to be running somewhere here in the curve.
What are the axes on that curve? What are the
That would be resonance.
and what are the parameters on that curve? I mean, is that current against voltage?
Yes,
or?
that would be where the motor's running the fastest with the least amount of current.
Okay.
So we want to be in the bell curve. We don't want to be running the motor down here. We don't want this flattened off. I don't.
I'm still confused by
Well, I'm gonna
okay.
look. This motor runs at what we call into a resonant point,
So that's
where it's the
RPM.
fastest it can go.
Okay.
This is the fastest RPM it can go with the least amount of current. Okay? So we want to be running somewhere in here. We don't want to be running here, and we don't want to be running here. If we're running here, you're going to burn the motor up. It's going to smoke the transistor. It's going to get hot. We don't want anything hot. So we don't want the coil hot. We don't want the transistor hot. We want this to run right here in this bell curve, which is max speed, least amount of current. And you can tell by tuning this resistor down here. If you move down and speed up, then 680 ohms was too much. If you move up and the current goes down and the motor speeds up, then that means that's the least amount. That means that the pulse to this motor is very sharp and very quick. And that's where we want to be. We want to be at the very sharpest pulse we can get, the sharpest transient. So, the next thing is now we have our basic circuit. So what we have here is something that's waiting to be triggered. It's like a magneto. The magnet has to come in here, has to charge the iron, there has to be a discharge take place, transistor turns on, rotor gets kicked away. Okay, now a lot of people ask, well, what are the degrees of that? Well, this can vary on how many poles that you have. But a good rule of thumb is just take this point and watch the motor once it's tuned, and you'll find out that it's probably coming in, charging the iron, leaving, and firing right here. So it's after. It's after top dead center. And this can be anywhere from 2 degrees all the way to 23 degrees. So if you just look at it, as if you have a bunch of magnets, around here, if you take these and center them all, it's always going to be after the fact. So if the motor's turning this way, it's going to be over here. 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 And so on. All the way around. Well, what are you going to do if you have 8 magnets and this is, say, 15 degrees? See, we're only taking the degrees, not the entire circumference of the wheel. We're only taking the degrees between the center of this magnet and where it fires.
So really during the work cycle.
Right.
Yeah.
Right.
So which is where the confusion arose. Because,
this is where the confusion arose.
Right.
I wanted to clarify that. These are the degrees you're looking for. Okay, and when you're in resonance, this will be at the furthest point. So you may be 18 degrees, you may be 23 degrees, depending on how big this wheel is. Because wheel size also makes a difference. There's no true set timing for this machine. It times itself. And the reason that it times itself is it's self-servoing to the load. So, we have the motor running. We have a 2-pole motor running. It's running now with this circuit. So, this battery is indicated by this battery here. I'm going to put another battery down here.
Do not put another battery?
No, put another battery.
Okay.
Okay, so now what we want to do is we want this machine to run, and we want this machine to convert energy for us to a different form of energy, because you're not going to get this battery at 12 volts to charge this battery at 12 volts. So you have to convert the energy to do it. So what we do is we just put a diode here. And we put it to the positive pole. and we take the negative pole and come back up here to the positive. See how that works?
Yeah.
So that's the second battery, right?
That's the second battery.
Right.
Okay, so what's actually happening here is, if you really analyze the whole situation, is you're using a little bitty signal to build a 24 volt pulse because you have two 12 volt batteries.
Right.
Okay? So, what we're looking for in this pulse, and sorry about the motor, what we're looking for in this pulse is something that sort of looks like this. And if the windings are correct and the resistor is correct, this should be at about 300 volts.
So this is the H wave?
Yes. Not all will look like H-wave because no one knows exactly what they're going to use for a core and what they're going to use for magnet. Now I'm going to make this one statement here. Do not use neo magnets. Use ferrite magnets. I've probably said this 1,000 times, and now I'm telling you, do not use the neo magnets because you're going to saturate this. This is going to be at the wrong distance between here and here, and you're going to fail. And that's all there is to it. You're just going to fail. What you want is a ferrite magnet here, a number 8 ferrite magnet. So I'm clarifying this for you. That's what I want. I want a ferrite magnet. I don't want a neo magnet. So I'm looking at voltages between 90 and 300 volts. Now, for all you interested in, well, I can't measure anything here with a meter. Well, why can't you? Why? Because you're only dealing with this. This little spike right here. It's not very big at all, is it? But what it is a hammer blow to this battery.
To which battery? Sorry, I missed it.
To the second battery down here. This causes a sharp transient to end up on this battery. Because this battery, battery A, this is A, and this is B. Battery A just supplies a trigger current for this device. Because what we want to do is we want to trigger the energy out of the field that builds in this coil. And we want to send that back to this battery. So actually what we want to send back to that battery is all these little spikes that actually look like this. Because that's the only thing you're going to see over the battery. And you're probably not going to see them at all because the impedance is so low here that the chemical is going to absorb it. Now, I'm not looking for current here. And one way to test this is put a 1 ohm resistor, take this battery out and just put a 1 ohm resistor here in between these 2 points. And if you are developing current, your machine is running incorrectly. All right.
Have you got any notions as to why it would be producing current? Why it would be, what would be
Yes,
incorrect?
something would be staying on here.
Okay.
Or this would be at much too low of a resistance, or this transistor would be leaking, or the diode's leaking. So since we don't know what components they're going to use, I can't answer the question of which one's going to leak. So
But these are common.
these are common things.
Yeah.
So let's look at our motor again. let's look at the real motor. So you can see exactly what we're after here. Okay, I'm just going to use the one that we built. I'm going to turn it sideways like this. I'm going to show you that if I disconnect the output battery, the signal that I'm looking for is right here.
So that would be battery B you've just disconnected.
Yes. I'm looking for this. I've got neon lights here so you can see the high voltage that I'm looking for. And you can hear it. Okay, now, notice when I walk around the machine, I want you to see here that the high voltage does occur. You see it here? So when I connect this up, well, I'm going to demonstrate something to you first. We'll stop the motor. And we'll just take these lights. We won't face them towards the camera.
That's okay.
This is a 13 amp hour battery, and that's what I want you to use on the machine to test and to find out how the machine works until you get it into sync. So what we're going to do is we're going to tell it, deplete this battery. So these are like 60 watts a piece on that 13 amp hour battery. And we want them to deplete it, so it might take us a few minutes to get them depleted. And then we're going to just charge them back up and hook the lights back up. The battery's starting to deplete. And we want to take this right to dead. And I don't like to do this, but with an explanation on the monopole, I feel it's necessary at this time to show you the capability of the machine. If I completely deplete this 13 amp hour battery right here, I take every bit of joules out of it with these lights. And then I wait a minute or two and I come right back and deplete it again because batteries do recover. It's the same thing that would happen if you left your lights on your car. It would deplete your battery. You went to start your car, it wouldn't start.
So we're gradually almost to the point where the battery is completely flat.
Correct, but we're going to get this down to where they're orange.
Just barely see them now.
Mm-hmm. Okay, so now what I'm going to do is I'm going to let them recover just for a second here.
So you took the lead off.
So I took the lead off to let the battery, and you can notice that the battery is sort of, you can feel sort of a little bit of heat because we've taken all the energy out of it. So if you'll come around here for a minute, and I'll show you the recovery here. This would be the same thing as if you went in a parking lot and turned off your lights on your car and gave it a little bit of time. The battery would recover and you would get this. So you might start. But you can see that's not recovering very well.
Bring it right down, yeah.
Yeah. So we're pretty dead. I've taken all the energy out of that battery. And now I'm going to go back to my explanation once again that this energy right here and that little tick that you hear is the triggering. So now we're going to go ahead and I'm going to show you here that we're going to still get the same spark. See it?
Yep.
So now we're just going to put that on there and you notice that
And that is, which battery is that, A or B?
this is B.
Okay.
And you notice the lights have extinguished here. They're out. And that the motor's starting to accelerate. Because what is happening here is the motor is automatically adjusting to what the impedance of this battery is. So all these little spikes every time this motor switches, we're getting this spike and it's going like this. And we're catching this energy here. We don't care about this because it's at 12 volts. And 12 volts could only divide between the two batteries. If it was leaking through there, you would get a little bit of charge in each battery.
So what's the maximum voltage of the spike?
So the maximum voltage of the spike is over 90 volts because these lights are coming on and killing it at 90 volts because we don't want to blast a hole in these transistors.
So the neon lights actually curtail?
They're bringing it down to a 90 volt. In other words, if it goes over 90 volts, the light is coming on, the gas discharge.
Okay.
Because I'm only interested in these spikes. I'm not interested in a current meter between this and there because I'm not dealing with current here. I'm changing the form of energy. I'm asking the machine to do work, which it's doing with a fan. That has to go into the equation. The work must go into the equation. The machine is doing work. While it's doing the work, I'm asking it to recharge its battery that we just depleted with the lights. Now there's no other way around this. We've taken this battery, we've drawn all the power out. So this is not trickery. And because you can see that if I take this lead off, the lights come back on. And look over here. It's really there. So now what I'm telling these spikes to do is go hammer the battery here and move the ions backwards as if the battery wasn't used. Now, how do I know that it's working this way right now? Very simple. Because that would never recover that fast in your car. But remember that it's going to take time to put all the energy back in that battery.
Right.
So this is how I know that it's working so far. I know that that battery over there is being depleted at approximately about 1/2 of an amp because that's where I have the machine set. It's a multi-pole machine. So we'll let it run for about 15 minutes and then we'll measure it out. You want another shot of this?
Yeah, I would actually. It's a great shot, actually.
Of that.
It's pretty good. That's good. One question, John, about the about these lights here.
Mm-hmm.
You say they cut the voltage off at 90 volts.
Yeah, they cut the voltage off at
when you-
90 volts because we're protecting the devices if there's no battery on it.
Yeah, my question is, when you buy these, I mean, is that in the specifications you say?
Yes.
You order, it's what, a 90 volt?
No, it's just an NE2 neon bulb and they're 90 volts, they light.
Okay.
So it's a standard item off the shelf. You can see this is what I drew on the board. It's a multi-arrangement motor, meaning that there's a bunch of number 23 wire here for, I think, about 150 feet on this one. So the wires were stretched out, maybe a little bit more than that, maybe about 300 feet.
How many wires are wound together there?
Well, you see here you've got 1, 2, 3, 4, 5, 6, 7 devices.
So 7 wires.
So 8 wires,
Oh, 8
because
wires.
you have one trigger circuit. And each one of these collectors is summed with a diode to a bus, and then that bus is right back off here. This bus is then to this positive pole, and then this negative pole is right back to the positive. So technically, this battery is across this coil. Is isolated by this coil.
And the little purple things are the resistors?
Yeah, these are the resistors, and of course these are 900 ohms. No, these are 470 ohms each. That's where this motor got into resonance. That's where it's running right now.
So the value of those drives the resonance point.
Yes, this selects the amount of current through the coil and the fastest speed of the motor. And it's giving you, actually this was chosen to give you the least amount of current and the fastest speed. And I want to make that point again, that we want to be in this curve, in this bell curve, and we want to be about right here. Max RPM, least current in this spike. We don't want a real fat spike because that's current. We want to keep it towards the Tesla technology, which is impulse, which is just this. And then we want to catch every one of these spikes and send it to this battery B. So we've been running about 4 minutes, I think, on this battery. But we've taken every bit of energy out of the battery. So we're asking this machine to recharge this battery very fast, which it's not going to do, because to put all those joules back in there is going to take a certain amount of time at this level. But it's putting it back faster here than it's actually depleting here. Because remember, we're using battery A for the trigger. Now the other thing is that if you can get your motor to do this and you follow directions completely, where no neomagnets, no solid bolt for a pole piece, your motor will run like this. It's up to you to make your motor to run like this. You know, many times I've stated on all the groups that I don't want any neomagnets. So I don't bother asking those questions. I don't answer those questions for the simple fact that I've said 100 times that I don't want any neomagnets. It's not an, I can't afford to do that here. It has to be a ferrite number 8 magnet because we don't want to saturate this pole piece. If you saturate this pole piece, then the current's completely different in here. It takes too much for the motor to turn itself. I want this motor to turn as easy as possible with the most amount of torque. Like I'm torquing it right here, and so is the fan. And you can see I can torque and torque and torque with my fingers. And I can get it down to where it's a stall speed. But even at this torque, this is the torque range of the motor, be 1/3 of its RPM. That's about 23% there. Plus it's pulling the fan. So I want to stress, what isn't understood is usually can't work. So once you understand the machine and what the operation and the principle of the machine is, then it should become crystal clear to anybody that's working on the machine that this is the way that it operates. This is the way it was designed. It was designed to use a primary battery to give you an impulse current, and what you're doing is you're creating that impulse current, which is a spike, and you're changing that form of energy that's a current into a form of energy that's not a current, because we don't want any current over here to charge this battery. We want this battery to charge cool. We want it to build energy on the ions and have the ions move themselves. So again, I can't stress enough to you all that it's up to you to make it work. I've made this as clear as possible with most of the groups, and I've made this as clear as possible now on this video, that this is the way I want the motor built. Don't change anything until you get it to work. Because if you change it and it doesn't work, you're going to say to yourself, oh my, it doesn't work.
Therefore it can't work.
Yeah, therefore it can't work. But you are very wrong when you think for a moment that this can't work, because we'll see where we're at right now. Now, what this actually is, and I want you to see here, load A is 0.4 ohms average.
Okay.
Now, can the motor light 0.4 ohms? Do you see any light? Because there's no current. But look.
Yeah.
What did I say in the beginning when I was talking about this motor? I said if you can drive, if you heat up the 1 ohm resistor, your motor is not working. So this is 0.4 ohms.
So what exactly is your point?
My point is that if there's any current in the output, it's not functioning properly. So here, is it charging the battery? I would say so.
Yeah.
Now there's a good explanation that this motor works. And that if it doesn't work for you, you built it wrong. That would start your car. That would start your car up enough
Yeah.
to get you started. So I want you people all to think about that out there. I want you to think about building a little motor with a little battery that if you depleted your car battery and left your lights on, you could go back in the restaurant and get yourself a beer or whatever you're going to do and start your little monopole motor and come out and start your car. Because it'll do it every time.
John, what are the some of the most common mistakes that people make? I mean, the top three,
The
top
common
five.
mistakes are magnets, number one. The spacing, number two.
Spacing between
You
what?
want the spacing to be about the thickness of the magnet. See? I don't want to really stop it because I want to.
No, I got it right
I don't
here.
want to deplete them. I want to go ahead and charge the battery, but I want it to about the spacing of these magnets. They're about
Oh, the spacing
Yeah.
between the
Yeah.
magnet. Yeah. Okay.
Yeah.
Okay, not the spacing. Yeah.
the spacing that and the magnet space. The thickness of the magnet is about the space you want between the pole and the magnet.
Right.
Oh, you mean the
Yeah,
wheel where it
yeah,
crosses
yes,
itself.
right. And that will put you in the ballpark. You might have to adjust a little bit one way or another way. The next mistake people make is they start out with a 10 ohm resistor because they can't get it to spin because they use neomagnets. And then they get on the group or they get it or they call and they say, I can't get it to run. It burned out my transistor. And then I said, well, what do you use for magnets? And they go, neomagnets. That's a misconception because a neomagnet's not exactly what you want for this kind of motor. So, next
What
mistake.
exactly is a neomagnet?
A neomagnet is a neodymium iron boron magnet. One of these things. One of these tough little magnets over here.
Okay.
It's an iron boron magnet. It's known as the General Motors magnet. And we don't want this because this is an iron magnet.
Neodymium.
Yeah. Yeah. We don't want this kind of magnet. This kind of magnet, when you put it next to aluminum like this, it becomes magnetic.
Okay.
Okay, there's too many field lines, and it's going to saturate this core, and it's going to take a lot of current
This is finished.
to get this up. Okay, but one of the other questions that I get all the time is, well, it's a generator, isn't it? No, it's not a generator, because if it was a generator, I couldn't spin it like this and take the outputs and go like that. It wouldn't continue to rotate. It'd stop.
You wouldn't get sparks
Right.
either.
I wouldn't get anything. If it was a generator, it was rotating this fast. You don't see any sparks at all.
Right.
But when you turn it into an energizer with the trigger, then you get this different form of energy. And I'm telling you all right now, it's a different form of energy. Battery A is not battery B. Battery B cannot go where battery A goes, because they're two different forms of charges. Battery B performs like battery A with lights, motors, inverters. So you could take an inverter with battery B and run it to A because it's the same kind of electricity. That's the other question that I get. The other question that I get is, why can't I use a bolt? Well, you can't use a bolt in here because you're gonna take the magnetic field and make it heat. It's going to require more current to make this machine operate at its resonant speed that you see it doing.
So can I ask a question then on that little drum you've got there with the wire wrapped around it?
Yes, the coil
Yeah. Where are the rods down the middle?
down the center of it.
Down the hole?
Yeah, the rods are as if it's actually a bobbin.
Mm-hmm.
And the rods are right through the center of this bobbin. Then they're sanded off.
So they
And
go
this
through the hole in the middle of the bobbin?
Yeah, there's a plastic hole right here in the middle of the
Right,
bobbin.
okay.
And it's like this, it's molded.
Right, okay.
And then we want all our multi-strand wires, we want wound around this.
Right, okay.
So we want,
So do you cram the center of that bobbin
yes,
with as many?
as many as you can get in
Okay.
here, and then you glue them.
Okay,
And then you sand it off so it's nice and flat.
Mm-hmm.
So you get a flat mounting surface that you can mount to.
okay.
And we want welding rod. We want iron rods, and the best
Oh,
thing,
yeah, I see that. Yeah.
the best thing to use is welding rod. Where do I get the welding rod? Well, you get the welding rod at a welding store, and you want the thinnest welding rod that you can get. And I think what you're looking at here is Lincoln Electric Mild Steel 1/16 by 36 R60. Believe me, 2 pounds of this welding rod is enough to do quite a few little motors. But you can see what it is.
So for somebody starting from scratch, what sort of money are they going to have to outlay to get the welding rods and the
If they want to
wire?
build a good motor and they want to use a bicycle wheel and they want bearings and they want to do it, like you see, just figure you're laying out $100
Okay,
to learn.
yeah.
After you learn, then you can expand on the motor. But like I said, it's up to the individual that's building this motor, because some will build it with expertise. Some will build it in the mid-range somewhere, and some won't build it very well at all, and it won't rotate correctly.
So another question, these are kind of like fuses, little neon lights?
No, these are neon gas
Right,
discharge
but
lights.
they effectively are like a fuse because a fuse will blow
No,
it.
the neon light,
How do they protect it?
when the spike hits 90 volts, that neon light, right, has a gas in this tube, and it discharges and lights up.
Oh, okay.
And that's what you're seeing right here.
So they're not protecting anything really,
No,
they're
they're
just,
cutting off.
they're cutting off, yeah.
The limiters, voltage limiters.
Yeah.
Yeah, they're
Yeah.
voltage limiters for the transistors, because we don't want the reverse spike to go back through the base circuit. So what we want is, we want to, when the second battery is disconnected, we want to limit this 300 volt spike to 90 volts.
Right, okay, got it.
See, because when the battery's disconnected, there's no way possible into the load that you could have any current. So therefore, if you don't have the current, you're not going to reach the 90 volts. The light's not going to light. So that shows you right there that you're not reaching any current level. Otherwise, it'd be lighting like this.
Yeah.
This impedance would have to be close to infinite for that to light. Have to be a battery that wasn't a battery. It'd be like taking this battery right here that has no solution in it and saying, please charge.
It's not charging.
No, because there's no impedance. So but this is protecting, it's limiting what the circuit's doing.
Okay.
battery B, can you put a second battery on that side?
Yes, you can put another battery here if you want. Just take longer to charge.
So you can wind up charging 2 batteries on that end.
You could wind up
4.
charging a whole bank of batteries if the machine was big enough and the trigger signal is correct.
Okay.
And this battery has enough amp hours in it to do it.
And hypothetically, how
Well,
big?
hypothetically, you've never seen a machine like this,
Right.
because this is the kind of machine where if you're looking at it as a toy or a fan in your living room, right? It's a kind of fan that's a regenerative fan, because you're not wasting any energy here. You're putting it over here.
Right.
Everything that's being thrown out into space, you're collecting, and you're not wasting a damn thing. So, you've never seen a machine like this. There has
Right.
never been a machine like this. You don't buy toys that come in those little boxes, and you put a battery in them, right? And as soon as your battery's done, you go in and you say, "Dad, my battery's no good no more." Well, if they did the toy right, you could take this battery theoretically, and your toy would keep running. So you've never seen this kind of a machine anywhere. Maybe in a different planet somewhere. I don't know.
Hypothetically, how big could this machine be scaled up to be?
To a Ferris wheel size.
Okay.
Any size that your imagination would like to take you to, you could do it. You could probably, and by the way, this takes into the theory, where Tom Bearden says that a flashlight battery could run a battleship. It could, theoretically. Because all you're asking is for the trigger.
Mm-hmm.
So if I take a 9-volt transistor radio battery and I put it right here, well, I can still run this machine. And I've got a little battery that's this big. So anyway, we depleted this battery, and now we're going to check it because we drained it to 0. And to prove that the machine is actually charging the battery, we're going to disconnect. And once again, you can see the lights saying that the battery is disconnected from it. And you can see it here. Okay.
Flash it again. Okay, the lights are flashing.
Yes, which means the battery's disconnected. Now we're going to see what's in the battery. Okay, so we let our battery charge, and we had depleted this battery, and there we go. We have our battery back. So it's absolutely possible to recharge the battery with no current, because once again, I'm going to do this. I'm going to take the leads from the motor and connect it to the lights. The lights go out and there's no current there.
Lights go out here.
Mm-hmm.
And
There's no light here.
right.
So therefore, there's no energy in current to charge that battery except for these small, minute spikes. So, you've got to be creative when you're dealing with this type of energy. I only have this or I only have that, so what am I going to do? Am I just going to stand there and do nothing and say it doesn't work? Well, that's what most do. But I'm not going to do that. See, I'm going to find a way to get the power out of something through whatever means I have to use to get it. Because after all, I don't have any energy now and the lights are up.
as
I
a
need to
car.
charge this battery.